Similar to arithmetic sequence, there is also geometric means. Check out some examples of finding this out here in Mathematics of Engineering. Like arithmetic means discussed in the previous video, geometric sequences also have means. In sequence like 3, 6, 12, 24, and 48, 3 is the initial term, and 48 is the final term. Such first and last values in the sequence are what we term as geometric extremes, and terms as 6, 12, and 24, or those within the extremes, are called geometric means. The first example showcases the solution on looking for the geometric mean between 16 and 1. If we notate 16 as the first term, a sub 1, and 1 as the final term, a sub 3, we are tasked to determine a sub 2. Knowing two terms in the sequence and with the formula for the nth term, we can equate a sub 3 as a sub 1 times the common ratio raised to 3 minus 1. Plug values of a sub 1 and a sub 3, making the equation 1 is equal to 16 times r raised to 3 minus 1, or that is r squared is equal to 1 all over 16. Compute the value of r by taking the square root of the equation, and r comes out as 1/4. What we are figuring out is a sub 2, taken as a sub 1 multiplied by r raised to 2 minus 1. Substitute the initial term and the common ratio to make a sub 2 is equal to 16 times 1/4 raised to 2 minus 1, and get a sub 2 as 4. The second example requires three geometric means between the initial term 3125 and the final term, which is 5. In illustration, we have 3125 as a sub 1, followed by three means tagged as a sub 2, a sub 3, and a sub 4, then continued with 5 as a sub 5. From the explicit formula, we can equate a sub 5 with a sub 1 times r raised to 5 less 1. And plugging the given from the statement, we have 5 is equal to 3125 times r raised to 5 minus 1. Place constants together and simplify the exponent to get r raised to the 4th power is equal to 5 all over 3125, or that is 1 all over 625. We can solve the value of r by taking the 4th root of the equation, resulting to r equal to 1 all over 5. Knowing the common ratio, we can then compute for the unknowns, starting with a sub 2 as 3125 times 1/5 raised to 2 minus 1, which is 625. A sub 3, on the other hand, has 3125 times 1/5 raised to 3 minus 1, resulting to 125. And lastly, a sub 4 is computed just the same with 3125 times 1/5 raised to 4 minus 1, or that is 25. Example 3 requires the number of terms found in the sequence starting with 6 and ending with 1458, knowing the common ratio as 3. In illustration, we have 6 as a sub 1 and 1458 as a sub n. From the explicit formula, we can plug in the given to have 1458 is equal to 6 times 3 raised to n minus 1. By dividing everything by 6, we get 3 raised to n minus 1 is equal to 243. Since n is a part of the exponential expression, we cannot just divide or multiply any constant to extract it, but rather we use logarithms. If we take the logarithm of the equation, we can pull down the exponent to the quantity of n minus 1 multiplied by the logarithm of 3, and this is equal to the logarithm of 243. This is from the laws of logarithms. Now we divide the equation by logarithm of 3 to get n minus 1 is equal to 5. Transpose 1 to the other side to get n as 6. This is the total number of terms in the sequence. But we are looking for the number of terms between the extremes, or that is the means, which is just 2 deducted from n, making the means equal to 4.